Hey folks, you have made it to the last worksheet podcast. Hooray. So I'm going to try and do this as quickly as I can. If you look at HCl, they are both nonmetals. H is 2.1 and chlorine is 3.0. So this is polar. And F2, F is bonded to itself. It's obviously nonpolar. Right, so this is a dipole. So it's a dipole force versus nonpolar, so that would mean this is London dispersion forces that are holding it together. So the thing that holds together better is clearly the HCl, so it's going to have the higher boiling point. All right, carbon, hydrogen, fluorine, interesting. So if you think about this for a second, you're going to have to do carbon to fluorine to hydrogen to hydrogen to hydrogen. You should look at that and be able to say, yeah, that's definitely polar, which it's going to be. This is going to be a dipole. And you're going to look over here and say CH3OH. Right? And you're going to say, well, guys, I've got not sure. Well, look at what's going on here. Here you have, when you get another molecule near here, this is going to end up with fluorine going to carbon with 3 hydrogens going off this way. Right? Bottom line is what you have here is you have what we call hydrogen bonding. And that is stronger than a dipole. It's a special kind of dipole. Whereas over here, you are going to have a dipole because you're going to have this OH, and this part is going to definitely be polar. So this is dipole over here. Right? And we know that a hydrogen bond is stronger. So CH3F is definitely stronger. All right, the last one on here we have H2O, and we have oxygen, which is bonded to hydrogen, which is bonded to hydrogen. It is bent. All right, and since it's bent, because you got these 2 electron pairs sitting out here, that is going to tell you that this is hydrogen bonded, because again we have hydrogen, and we have the FON thing, the nitrogen, oxygen, fluorine, and in this case it's oxygen. So this is hydrogen bonding, and so that's pretty small, pretty large. And then we have H2S, right? They're all covalent, so we have sulfur, and we have 6, 7, 8. So we're going to have also something that looks very much like water, and it's polar. And we've got these 2 electrons up here. However, the hydrogen bond, hydrogen to oxygen, is stronger than just a regular dipole. All right. So this one over here is a dipole. One on the left is hydrogen bonding, so the stronger one is H2O. All right. SiO2. Silicon dioxide. So silicon is going to be in the middle, and it's going to look like this after you finally draw it. Right? And SO2 is going to be S to O to O, and you're going to have, let's see, you have 6, 12, 18. That's 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, that's 8, and 8 are 16. We have 17, 18. In order to put another one up there, we have to turn one of those and get rid of it. So that's what we have. Okay, so we have something here that's bent, right? And so this is definitely polar, right? Your difference between sulfur and oxygen is a full 1, but just the shape makes it polar. So it's a dipole. And the other one is definitely not, because you have the same thing on either end, so I don't have to bother wasting my time. Right? Since I have the same thing on either end, let's see, I guess this is going to be, well, now wait a minute. This is silicon dioxide. Hold on, that's something special. Silicon dioxide is a network solid. And those are very, very, very strong. Remember, we talked about silicon dioxide being glass. So network solid's very, very strong. So this one is going to end up with the higher boiling point, even though this is a dipole. So this will be SiO2. Almost missed that one. All right, iron is clearly metallic. And krypton is clearly a noble gas. If krypton's a noble gas, it bonds with nothing. All right? So when it's with other krypton gas atoms, it's the only thing that's going to hold these two things together are London dispersion forces. So I have metallic versus London dispersion. Clearly, it's going to be the metallic one. It's stronger. Right? Now here I have copper and oxygen. That's ionic. I can just look at it. And this is going to be some form of covalent. I don't know if it's going to be polar. I think it is, but frankly, I don't care. Ionic is much stronger, so it's going to be CuO. So I don't even have to waste time doing that. All right. Now these top two are both covalent, so I have to look at NH3. NH3 is going to look like this. So that means it's going to be polar, so this is a dipole. But remember that when you have hydrogen bonding, it has to be either an N, an O, or an F. So it will be. So we're going to call this one hydrogen bonding, which is pretty small, pretty tight, rather, pretty good. CH4. CH4 is going to be completely nonpolar. And since it is nonpolar, this is going to require, when you try and put it together, it's going to require London dispersion forces to hold these together. So the hydrogen bond one is much stronger, so NH3. Right. If you happen to know what these things were, that would make sense, because NH3 is ammonia, and CH4 is natural gas. And so, obviously, ammonia is a liquid, so that's clearly stronger. Right. HCl is a gas, and NaCl, you should know that it's a solid, it's ionic. This is clearly covalent of some sort. So HCl is going to be a 2.1 to 3.0, so this is going to be a dipole. And clearly ionic is stronger, so it's NaCl. And let's see, silicon bonded to carbon. Silicon bonded to carbon. Wow. I would say I have carbon is supposed to be a network solid. Right, so I would say that this is a network solid over here. Because it has silicon and carbon, and they both make 4 bonds, and they're both doing the tetrahedral thing. So I'm going to say that's a network solid. And over here on the right, this is metallic. Right, and metallic forces are holding it together, so they're pretty strong, but the network solid is stronger, so it's SiC that's going to be stronger. All right. So let's rank the following substances from lowest to highest boiling point. Lowest boiling point means it is not held together well. So London dispersion forces are what we're looking for the lowest one. And for the top one, we're going to be looking for something like a network solid. And in the absence of a network solid, we're going to be looking for an ionic compound. All right. So let's look at what we have. We are looking for a network solid first. Do we have one? I don't see one. Do we have something that that is then ionic? Yes, we do. We have NaCl, which is ionic, so that is going to hold together really well. And now we're looking for something that is metallic, which is our next lowest one, and that's Ag. And then we're looking for something with hydrogen bonding. Well, we have hydrogen bonding here, so that's going to be H2O. And then we're going to have a dipole, and a dipole would be HBr. And then we are getting into the things that are held together by London dispersion forces, right? And very weak forces. And helium, because it doesn't bond with anything, is going to be the weakest over here. And then CO2 is going to go in the middle. Okay? Lowest to highest boiling point. Well, what do we have? Well, we do not have any. We do not have a network solid, but we do have a metal, and we do have an ionic compound. So the ionic compound is going to be last. Ca3, PO4, 2. Bottom line, guys, on your ionic compound, you can see that that's a metal and that's a non-metal. So we can tell that it's ionic. We have chromium here, which takes care of that one. We now have water, which has hydrogen bonding in it, which is H2O. And then we're going down to our last two, which are, both covalent, which is these two over here. But OF2 is bent, so OF2 is going to be next. And then C2H6 is completely nonpolar, so we're going to have C2H6 being our least one. All right, and here's our last one. Our last one, we're starting at highest to lowest. We are actually ranking this backwards to what we just did, right? So our highest one is going to be diamond because it's a network solid, right? And our lowest is going to be neon, because I can just look at neon and say it's a noble gas, which is held together by London dispersion forces only. I have chromium hydroxide as ionic. I should then have metallic. I do. I have calcium, which is metallic. So it's done. I then have to go between Cl2 and this long thing over here. And I'm definitely going to go with this long thing over here because I have more opportunity for some kind of holding together, some dipole, where with Cl2 I never have the opportunity for a dipole. So it's going to be CH3, CH2, OH. And then my last one is going to be Cl2 before I get to neon. Okay? So, I think that's it. It is. We are done with all these podcasts and all these worksheets. If you have questions, please see me in class. I'll see you then. Bye-bye.